Welcome to the TI Precision Lab presentations. My name is Anthony Lodi, and we will be discussing peak versus RMS current and how it relates to motor drivers. The topics we will be covering today are: what is peak current? What is RMS current? Why is peak current important? What role does RMS current play in driving a motor? We will also cover the differences of RMS currents in brushed, stepper, and brushless DC motors. Finally, we will discuss current protection features that are found in many TI motor driver devices. To start off, let us look at an example that may help in understanding the concept of peak versus root mean squared current, also known as RMS current. Many people are aware that most outlets around the house in the United States are 120 volts AC. This does not mean that the maximum voltage is 120 volts. Rather, this is the RMS value. The actual voltage is sinusoidal in shape and varies from about plus 170 volts to minus 170 volts. So for a standard 120 volt outlet, the peak value is 170 volts, but the RMS value is 120 volts. In this presentation, the focus is about learning how RMS and peak current relates to motor drivers, so we are more interested in direct current or DC applications, not alternating current or AC as in this example. Peak current can be defined in this way. Peak current is the maximum current at a given point in time. RMS currents, on the other hand, can be defined as the average current over time. RMS current can be calculated mathematically from any waveform, not just a sinusoidal waveform. In the plot on the right, the current peaks at a certain point in time and then starts to decay to a more constant current. When discussing RMS current, the part that matters more is the amplitude of the current when the current has become steady. RMS current is helpful when calculating power consumption, since the average current can be used in the formula power is equal to the square of the current times resistance. One thing to note, in this presentation we will be discussing the peak and RMS current flow through the stator windings of a motor, not the current that is supplied from the power source of the system. So why is peak current important? Current spikes are common when driving a motor, especially as a result of the frequent on and off switching of the transistors. Peak current events can be set and controlled by the driver, or they can be a result of a condition such as overcurrent. It is important to monitor peak current to avoid damaging external components and the gate driver. There are a few conditions that can be particularly hazardous to the safety of the device. One event, called shoot-through, is extremely dangerous to the system. Shoot-through occurs when both the high side and low side of a half bridge are on at the same time, as shown in the animation on the bottom right. This creates an extremely low resistance path to ground through the MOSFETs, causing dangerously high current flow in the system, which can cause damage to the components. This type of current spike can also occur if there is an external short on one of the components. Another event that can cause high current is when the rotor of a speed-controlled motor is suddenly stalled during operation by an external force. Since the gate driver is attempting to maintain a certain speed, the controller will rapidly increase the current through the phase windings to increase the torque on the rotor to move it to the next position. This rapid increase in current can cause the current ratings of the motor to be exceeded, which can damage the motor and other components. The third event that can produce a current spike occurs at startup, since the motor needs to overcome the inertia that is present to get up to speed quickly. This results in the motor driver supplying higher current to increase the torque to bring the motor up to speed. Why is it important to know about RMS current? RMS current is important because the current through the stator windings produces the magnetic field that is necessary to spin the rotor. Since RMS deals with the average current flowing through the coils, RMS current can tell us the average strength of the magnetic field that the coils produce. Another important reason to be familiar with RMS current is that the current through the stator windings is directly proportional to the torque of the motor. A motor driver must be able to regulate the current to achieve the desired torque that is needed to move or hold a load. This is especially relevant in stepper and brushless DC motors since they are commonly used in many torque control applications. Let us take a moment to discuss the method that is used to change the RMS current supplied to a motor. Pulse width modulation, also known as PWM signals, are used to control the average current through the motor windings. PWM signals are used to switch the H-bridge MOSFETs on and off at a certain rate to achieve a desired average current. The duty cycle of the PWM signal can be adjusted to change the RMS current. An example of what a PWM signal looks like is shown on the bottom right. RMS current can be calculated mathematically from the shape of the current waveform using the root mean squared formula. However, RMS calculations can quickly become complex if the user does not have access to the appropriate software or calculators to aid in computing the RMS value from the current waveforms. Another method to determine the RMS current is to use a power meter to measure the RMS current. This method removes the complications of the mathematical computations and provides a quick way to obtain the RMS current value in real time. RMS current can be controlled in brushed DC motors by adjusting the PWM duty cycle to achieve a desired torque for the motor. Changing the PWM duty cycle will also change the speed of the motor, since the higher current produces a stronger magnetic field in the motor, which results in higher speed. The image on the bottom right shows the current through the coil windings of a brushed DC motor at the initial startup of the motor. There is a peak current event. Then the current decays to a constant RMS current. To find out more info on brushed DC motors and motor control, visit the Motor Drivers Brushed DC Motors section of this training series. For stepper motors, current plays an important role in motor commutation. A stepper motor has two pairs of windings, and stepping through different current levels in each stator winding causes the rotor to move to a desired position. Stepper motors are used many times in position control applications, and it is therefore necessary to move the rotor to a particular angle and hold that position. This is achieved by changing the current through the coil windings to create the necessary magnetic field between the coils to move the rotor to the appropriate position. One interesting thing about a stepper motor is that the total RMS current at any point in time is the same. This is because the sum of the current through each winding adds up to the same value, no matter what stage of commutation it is in. For example, if the current through winding A is 70% of its peak value, then the current through winding B will be 30% of its peak value. So the total RMS current is the same as the maximum continuous current in the coils. To find out more information on stepper motor commutation and the importance of current, visit the Motor Drivers Stepper Motors section of this training series. There are two types of brushless DC motors, trapezoidal and sinusoidal motors. These different motor types require different current waveforms to efficiently spin the motor. As the name suggests, the current through the phases of a sinusoidal BLDC motor is sinusoidal in shape. The RMS value of a particular phase can be calculated by the peak current divided by the square root of 2. For trapezoidal BLDC motors, the current through the windings is switched from positive current, then to an off state, then to negative current. The pattern is shown in the image on the bottom right. To find out more info on brushless DC motor commutation and the importance of current, visit the Motor Drivers Brushless DC Motors section of this training series. The last topic we will discuss is a couple of the current protection features that are available in TI's motor drivers. One protection feature is called overcurrent protection, which helps protect against dangerous peak current events. Overcurrent protection protects the motor driver from experiencing too much current by shutting down the device when the current through the windings exceeds a defined threshold. The overcurrent threshold is the maximum amount of current that can be pushed through a device before the overcurrent protection feature shuts down the device. Another protection feature in TI's drivers is thermal protection, which is related to RMS current. If the motor driver begins to heat up to dangerous levels, possibly due to a high current event, TI's motor drivers have a built-in protection feature that will shut down the device to prevent damage. For more information on more of the safety features that are available in TI motor drivers, visit the Motor Drivers Motor Technology section of this presentation series. To summarize, peak current is important to monitor since high peak current can damage the device. RMS current is important because it is related to the torque that the motor supplies to a load and is also useful when calculating how much power a motor uses. To find more motor driver technical resources and search products, please visit ti.com/motordrivers. Special thanks to all my colleagues who provided feedback to help improve this presentation.